Okay, time to get started. We will finish up our relativity today, and so we will start chapter 29 on Friday. So the first deadline date for concept coach questions for chapter 29, I know it said 29-1 today, but it won't be until Friday. So now we're 2 days behind the lecture schedule because I'm taking an extra day here on relativity. So let's finish up relativity. First by asking got to start this, you can't answer yet. A clicker question. Okay, so suppose Usain Bolt carries his own stopwatch, assuming both his stopwatch and the stopwatch of the official are exactly correct. How do the times compare for Usain to run the 400 meters, assuming a constant speed? This is ideas we've talked about in this past week, but we want to make sure that they've solidified a little bit before we leave relativity. Okay, Caitlin and Jerry. All right. We had a pretty strong agreement there, so let's have this person explain it to us. This person is Isaac.
I definitely called that.
Time to go vet in Vegas then.
I chose B because when we talked about reference frame, my train of thought is if Usain has his own stopwatch, his frame of reference is both at the start and the start and the end. So when he's running towards the end, his reference frame is the finish line is coming towards him.
Mm-hmm.
So his perception of time will be shorter as opposed to someone who's just standing at the finish line.
Okay, that you're absolutely right. Now, some things that, what would have made this problem easier to understand, it's hard for us to think about when I'm running, I'm stationary. But yet when we say his reference frame, we mean the reference frame that sees him as stationary. So it's hard for us to visualize that idea. And the ideas that he had were correct. If the clock is stationary in that reference frame, it's going to measure the proper time. Now, one thing we also have to keep in mind is we have the time dilation equation. Can both the person on Earth and Usain Bolt use that time dilation equation? No. Because Usain Bolt accelerated. He accelerated because he started from rest and sped up, and then he slowed down, but he slows down a lot less than other runners. But when he gets to the end, of course, after that, he's going to slow down again. But he had to accelerate. And if he goes in a circle, which the 400 meters does, 400 meters is doing a lap around the track, you also are changing direction, which is acceleration. So the person on Earth is going to make correct measurements, and they can use the time dilation equation, knowing that the clock that is with him is the one that's going to be measuring the proper time. Okay, now to addition of velocities. So we have two equations here for one picture. We have two people in their spaceship / bumper cars, and B there shoots out a probe. And so that probe is traveling at a speed of V sub PA. That means the speed of the probe as measured by person A, and B is traveling at speed V sub BA, where it's the speed of B as measured by person A. Well, how do I find the speed of the probe? I see that I put my equation with different. I thought that this said probe with respect to B when I wrote my equations. I'm just going to change that subscript so my equations are the ones that you need for this. So I'm just going to change that to a probe B. Speed of the probe with respect to B, because clearly she's the one who shot it. And so how fast is that probe moving as measured by Abe? if we were to use the Galilean transformation, we would say, well, the speed of the probe as measured by B plus the speed of B as measured by A is the speed of the probe as measured by A. It makes perfect sense. It's the same thing that we started out with. You have a person on an escalator, and the speed of the person relative to the Earth is the speed of the person on the escalator plus the speed of the escalator with respect to the Earth. But the problem is, what if B shoots this thing? So let's say speed of B with respect to A is equal to 0.75 c. And let's say the speed of the probe with respect to B is equal to 0.5 c. If we were to use the Galilean relativity, what speed would the probe be as measured by A? It'd be 1.25 c. But of our postulates of relativity, the second one was the speed of light in vacuum is a constant of c in all reference frames. And the first postulate was the laws of physics apply the same in all reference frames. And one of those laws of physics is nothing can exceed the speed of light. And so the speed of light is constant, and this is saying it's faster than that constant, not possible. So that means that our equation is broken. Now, we didn't quite get to the work yesterday in the calculus-based class for how we derive these equations. But as Einstein developed, the way to add the velocities is by taking, notice this thing on top is exactly the same as the Galilean equation. But we're dividing it by 1 plus the speed of the first object with respect to the first reference frame times the speed of that first reference frame with respect to the second reference frame. That's the two things that were on top. We multiply them together and divide by the speed of light squared. That will give us a different answer. So let's just put in these numbers. If we put in those numbers, we have the probe with respect to B was 0.75 c. B with respect to A was 0.50 c. I think those were the numbers, weren't they? Nope, backward. Well, it would be the same, but I want them to be in the right order. Now you notice why it's useful to have c as a unit for the speed of light. Because if we look down there in the numerator, or the denominator, 0.5 times 0.75, that's half of 0.75, so 0.375. C squared over c squared, the c squareds cancel out. So this is 1.25 c on top, divided by 1.375 on bottom. And so since I have my trusty calculator man, Jonathan, that you all should thank for doing your calculator work for you, what does that give us for the speed of the probe as measured by Abe?
0.91 c.
0.91 c. That does not violate any physics rules. And based on further theory, that's also the correct answer. Because right, I could just say, well, let's divide by some random number to make it so it stays less than speed of light. So that's how we add velocities. So what's the mechanism to remember this? You always, this is an example with light. If the probe was traveling the speed of light, I would have some crazy equation, 1, c plus whatever the speed is over 1 plus c times the speed over c squared. It always is going to turn out that light has a speed of c by this equation, regardless of what reference frame. So this also agrees with the rule that the speed of light in vacuum is the same in all inertial reference frames. Okay, but what I want to get to was this. What do we do in any case when we want to find the speed of one object with respect to another? We use this relationship that we have to have on top. These two indices have to be the same. That little cross out is to indicate that they're the same, and so in my mind they're collapsing out. And likewise, it's the same indices, so they're the same there. Now, the slide I skipped over is important. The slide I skipped forward says, it's just a reminder, if I am coming toward Hannah at a speed of 1 meter per second, as measured by Hannah, then if I measure it and I say I'm stationary, I'd say Hannah's coming toward me at a speed of 1 meter per second. So we both agree that the speed is 1 meter per second. What we disagree on is the direction. I said that Hannah was coming this way, and Hannah said I was going that way. So the directions are opposite, which means that the velocity is going to be in the opposite direction. So if we want to go from the speed of Hannah with respect to Richard to the speed of Richard with respect to Hannah, we flip the indice order and add a minus sign. So it's very simple to switch a speed from one reference frame to another if you're saying the speed of A with respect to B compared to the speed of B with respect to A. We have to use this addition if we're doing something more complicated, the speed of P with respect to A or the speed of P with respect to B. Then we have to use the more complicated equations. So let's do an example. Make sure we can do this. Two spaceships travel at high speed in the same direction along a straight line, as measured by an observer on the planet nearby. So here's my observer. Ship 1 is behind ship 2. So here's ship 1. These ships are amazingly brick-like in their behavior, or their looks. And ship 1 is moving at 0.90 c. So the speed of 1 with respect to the observer is equal to 0.90 c. And ship 2, with respect to that same observer, is 0.70 c. And now I want to find, according to an observer on ship 1, how fast is ship 2 moving? What's the subscript for the speed I'm looking for? Speed of which object? 2. So my first subscript is 2. With respect to which object? So I'm looking for V21. Using our equation, I need to throw the subscripts on there. So what should I have for the first set of subscripts? 2, observer 2, because the first item here was 2. So the first item there is 2. What about the second one? 1. 1, because the second item here is 1. The middle ones had to be the same. Why was it O? Well, because I have to have the same thing, and my measurements were made by the observer, as luck would have it. And then on bottom, I have the same subscripts there. So we look at the numbers. I have V20. This I already have. But I don't have V01. What do I have? V10. So how do I get V01? Right, it's just negative V10. And then I'm good to go. So there I put the direct substitution, V01 is equal to minus V10. I usually actually wouldn't do that. I would just say this is equal to minus 0.90 c. And so for my answer, I have 0.70 c minus 0.90 c divided by 1 plus 0.70 c times minus 0.90 c all over c squared. Notice the numerator here is minus 0.20 c. The denominator is 1 minus 0.63, because 7 times 9 is 63. So 0.20 C divided by 0.37 is?
Minus 0.54 C.
So the person on ship 1 sees ship 2 traveling which direction? Toward or away? Traveling toward them at a speed of just a little over half the speed of light. Even though the person on the observing planet saw them traveling at 0.70 C in the other direction. All of these are correct. Relativity is about how you relate the different reference frames' motion. Now, as I said before, this is only dealing, this equation that we've been doing here is only for parallel velocities. The Physics 252 students will learn about how to do it for perpendicular velocities, but Physics 152 will only be held responsible for the parallel velocity case. Okay, any questions about the addition of speed, how that works? Okay, I want to make sure I gave it time for somebody to, if you're like me, I'm at a meeting, they ask, does anybody have a comment? I'm still thinking. 2 minutes later, I'm all, yeah, if we could go back to that. Drives me crazy. Here's a picture to go along with the work we just did. It's a better picture than I made, but it's the same work. Okay, so now a simple question. A spaceship traveling at 0.5 C, as measured by Earth, fires a photon torpedo at a speed of C because it's photons. How fast does the photon torpedo travel as measured by Earth? Answer, Jerry. Okay, waiting for Jerry, Caitlin, and Isaac. Just Jerry and Caitlin. And Caitlin. Yeah. Sorry, yeah. Mine shows it's not. There we go. All right, now the numbers moved around a bit. We ended up with one person said 1.5 C, 16 said 1.0 C, 4 said 0.5 C, and 0 said it depends on the direction it's fired. So, Caitlin Toy, give us some light. Never been more unsure in your life. That's a, wow. It's a statement. Okay, well, let me ask you a simple question that will lead you to the right answer. How fast does light travel? With respect to who?
The spaceship, right?
What was the second postulate of relativity?
I'm confused what you're asking.
Okay, the second postulate of relativity says the speed of light in vacuum is the same to all inertial reference frames. So this question is asking how fast is the light traveling? Because a photon torpedo is light. How fast is light traveling? C, with respect to whom? Everyone. Wow. You even have the same inflection. That's a little scary. So I forgot to give Isaac a score. So the correct answer then was 1.0 C because it's the same for everybody. We didn't have to pull out the calculators to calculate it because that was a rule, a hard and fast rule. Now we could have pulled out the calculators. We could have said the speed of the torpedo with respect to Earth is equal to the speed of the torpedo with respect to the spacecraft plus speed of the spacecraft with respect to Earth. And if we put our numbers, that's going to be C plus 0.50 C over 1 plus C times 0.50 C divided by C squared. The top is 1.5 C. The bottom is 1.5. 1.5 divided by 1.5. Everyone here knows the answer, obviously. So we could have pulled out the old calculator and calculated and found that, yes, it was the speed of light. So, I would hope on a test, like I said, I put this question on a test before and had a lot of people who missed it. I would hope on a test you could just look at the postulates of relativity to answer it. It's the quicker way. But if you don't remember, you can go to this is the way velocities add and still get there. Less confused?
Oh, yes.
Excellent.
I have a question about that. So if you just put the postulates of relativity, therefore we don't need to have an equation for that.
Correct. And when I grade problems, sometimes I do it that way. You can do it with equations and calculation or without. Okay, Doppler shift. Doppler shift is something that I think we cut out first semester. Doppler shift is the effect of if something is moving toward you, then the space between peaks of the waves is shorter because it emits a wave here, the sound is traveling, and in the time that it takes for the sound to move one wavelength, the source has moved forward. And so it produces another peak here, but it's closer to the original peak than one wavelength. Because it's closer, that means that as traveling through the air, the sound wave has a shorter wavelength. And since frequency and wavelength are tied together by speed, that means the frequency had to shift upward. So if something is coming toward you and giving off a sound, the frequency is higher. If it's moving away from you, just the opposite. The distance between the peaks is longer, and so it shifts to a lower frequency. Hence, you have the effect of when something passes you. And when I came to America, did I talk about this at all first semester, or did I skip it? Okay. When I came to America, my parents were all like, he's an American, he's got to go to Disneyland, see, America. So here I am, a little 5 or 6 year old going. I was 5 when we came to America. We go to Disneyland, and we're riding on the People Mover, which it turns out, unless you're there with your girlfriend, is boring as all get out. But for a 5-year-old, it's super exciting. You're seeing everything in Disneyland. You're moving at a pace of 2 miles an hour, and then you go into the super speed tunnel. And the super speed tunnel, they blow air so you have the wind in your face. And they project on the walls things like motorcycles racing past you or cars racing past you. It shifts from one to the other. And you have the sounds going as they pass. And to a little 5-year-old like me, that was all of the physical evidence I needed to know that those were really cars racing past me. Right? If it hadn't had the sound, it wouldn't have been complete. Even my 5-year-old brain would have said something's missing here. But we've come to understand that Doppler effect by how we observe it. You have a car drive by and you hear it. So this was the equation for sound. Now notice, with sound, it's reasonably complicated. We have the speed of sound, so the speed of sound in air, and we have the speed the observer is moving, and we have the speed the source is moving. All those things come into the Doppler shift. With light, we have a Doppler shift again, but it's different. It's different because you don't have to worry about the motion of the observer and the source. You just have to worry about the relative motion between them, because the speed of light is the same in all reference frames if you're in vacuum. And so the equation comes out to be different. You also have to take into account the time dilation and length contraction to get to this formula. So the Doppler shift has a different function. Still the same idea of why it occurs, but because of time dilation, length contraction, and light traveling in a vacuum at the same speed in all reference frames, it's a different form. This here you might love or you might hate. You might love it because they will do things like, send out radar and look at the reflections back, and using Doppler shifts, determine how quickly water droplets in the atmosphere are moving. Right? That's where Doppler radar is. And so they're looking at the frequency of the radar they sent out, the radio waves, and the frequency of those reflected, and taking the relationship between those frequencies, they're calculating what the speed of the object is from that equation. That's good, right? Helps us plan ahead at least for 2 hours. But then there's the really evil side of this. As always, science can be used for good or for evil. And yes, the evil side is you're driving down the freeway, nothing in the world, and all of a sudden you get pulled over. Why? Because there was some dude sitting here with this little radar gun pointing it at you, and he is sending out a radio signal, and it reflects off your car, comes back to him, and then he has a little super heterodyne that is taking the two frequencies and mixing them together to find the difference in the two frequencies, and from the difference in the two frequencies, and knowing what frequency sent out, determining how fast you're traveling. And then they extract money from your wallet by applying physics. Yeah, it doesn't make me all that happy. Last time I got a ticket, I was a distracted driver. I was trying to get a wire on a note, and I wasn't looking at the speedometer. I feel so stupid. Okay, next one. So Doppler shift is different from non-relativistic, from sound, to relativity. This one here is probably surprising. The momentum equation that we learned is not correct. What's the equation that you learned for momentum in this class? Came from my mouth. You learned momentum is mass times velocity, and it's a vector. And now I'm telling you that that's not momentum. That's momentum if you have something traveling at a pedestrian speed, like, I don't know, let's say 5,000 miles per second, right? That would work fine. But if you get anywhere close to the speed of light, then that's, okay, I did 5,000 miles per second, might be pushing it. I don't know what the speed of light is in miles per second. Anybody here know? I know what it is in meters per second. It's 300 million meters per second. 5,000 miles should be about 1,000 times too low. So if you're going close to the speed of light, the equation for momentum changes. It becomes the same, but with a gamma in front. That gamma, the Lorentz factor, is a number that is 1 at low speeds. But as speed picks up, it starts getting larger. So that means as you get close to the speed of light, your momentum increases more and more as your speed hardly changes. Now this is actually an important thing. I said one of our rules is nothing can reach the speed of light. We can take this relationship and say, okay, our acceleration, according to Newton's second law, well, what is Newton's second law? Okay, I'm putting it in terms of change in momentum over change in time. So the net force is change in momentum over change in time. As the speed approaches infinity, or approaches the speed of light, what does gamma approach? We talked about in class, and you had it homework, I think, as well. Infinity. And so as your speed gets larger and larger, your gamma portion of momentum is approaching infinity. So your change in momentum, any change in momentum, is just going to get you infinitesimally closer to the speed of light. But you would actually have to have an infinite force to be able to force gamma to infinity And you can't have an infinite force, right? So with finite forces, you can never reach the speed of light because that gamma is going to blow up. Now, people in calculus class, we can write this as the most accurate dp dt, and then we will do some integration from that. So Newton's second law is no longer force equals mass times acceleration. It's no longer force equals mass times acceleration because of the gamma that was introduced in momentum. So if I were to write this as we have up here, that would be delta gamma mv over delta t. And notice gamma has velocity in it, so I can't move the gamma outside of that delta. It's not simple. I have to keep it in there. And in fact, I will show you, I think on the next slide, the integral of this, maybe on the next one after that. But Newton's second law is still correct in this form, just not in the net force is mass times acceleration. Paula.
You said that you can't have an infinite force. Why is that?
We don't have anything that could produce an infinite force.
So even
It's
with like planetary motion and things like that, because those are pretty big.
you would have to have the centers of two objects exactly the same place to have an infinite force. And that's not possible. It's good to point these things out and not just say, whatever. Okay, so everybody understands Newton's second law, why it's no longer sum of the forces mass times acceleration. The true Newton's second law is what I have in this equation. This here is the truest form of Newton's second law. And that's still perfectly correct. But net force is mass times acceleration was an approximation to Newton's second law, making certain assumptions. And if you're at relativistic speed, those assumptions fail and you can't use it. Okay, we're going to do a conservation momentum problem. I have a proton moving at 0.70 c. That's the V initial there. It has a head-on collision with a nitrogen nucleus and recoils at a speed of 0.63 c. How fast does the nitrogen move? Before relativity, what would you have done? Before relativity, what principle would you have used? Conservation momentum, you would have said momentum initial is equal momentum final. This is one-dimensional, so I'll just use plus and minus for my directions and drop vector signs. My momentum initial was just mass of a proton times V initial. My momentum final is, I'll put mass of a proton and minus V final because of the direction, plus mass of the nitrogen, speed of the nitrogen. And then I simply would have moved this over. That's how we would have done it non-relativistically. What would I have had for my answer? Well, nitrogen, it's nitrogen 14, it's 14 times the mass of a proton. So I would just have mass of the proton over 14 mass of the proton times 0.7 c plus 0.63 c. So that's equal to 1.33 c over 14. And what would we get?
0.0315. Sorry.
No? Yeah, because it should be somewhere close to 0.1.
Yeah, 0.095. Multiplied instead of that.
Okay, so we have about 0.095 c is what we would have calculated non-relativistically. But that's not correct because how do I know that's not correct? because they're moving at relativistic speeds. What defines a relativistic speed? Greater than about 1/10 the speed of light. So now let's do it relativistically. I gave myself not nearly enough room. It's always interesting to see, have they fixed it yet? No. Okay, so now we're going to do it relativistically. So we had V1 was 0.70 C. V2 is minus for the direction, 0.63 C. Mass nitrogen is equal to 14. Mass proton is all we need for that. If I'm doing it relativistically, what's the first thing I really need to calculate? Gammas. I need gamma 1 equals it's crashed. I've become very good at that. I think it had to do with my insert page and how that screen went blank. I think that was a precursor to the crashing, just in case you're wondering. .70 C over C is just 0.7. 0.7 squared is 0.49. I forgot this. I got the sign wrong here. That's a minus. 1 minus 0.49 is 0.51. Square root of 0.51, I don't know.
0.714.
Okay, and then 1 over that?
1.40.
So gamma 1 is 1.40, and what about gamma 2? No, it's technically minus 0.63, but minus 0.63 squared is the same as plus 0.63 squared. What do we get for that? Okay, so now we'll do our work. My momentum initial is going to be mass of the proton times gamma 1 V1, or V initial, equals minus mass of, well, I forgot if, yeah, put the minus sign out here. I have to put gamma nitrogen. I have to treat the nitrogen as relativistic as well. So now if I do my work, I'm going to have mass of the proton times gamma 1 V1, or VI, gamma 2 V5. So if I do that calculation, 1/14 of 1.40 times 0.70 C plus 1.29 times 0.63 C. What's that going to give us? Notice it is more complicated.
I got
0.128.
0.5.
That's additional digits? Okay. So that's what I get for gamma n Vn. I'm not actually done yet, because I need to actually calculate what the gamma is going to be. If that was less than about 0.1, I would have assumed gamma is just 1 and said my speed is approximately 0.128 C. But because it's bigger than 0.1, I'm going to go ahead and do the work. So now I have to expand that and say that's the equation. And so if I bring this inside, it's equal to that. But square both sides, move things across. Add 1 to both sides. Invert and square root. Yay, yay, yay. So you take that 0.12805, square it, invert it, add it to 1, invert again, and square root it.
0.1270.
And that makes perfect sense. It's just a little bit below what we had for gamma V, because, of course, gamma is going to be pretty close to 1 if we're pretty close to 0.1 C. So that's the full-on calculation. A little bit harder, right? Now, there are ways that we have of actually making these calculations surprisingly easy. And those come with looking at invariance, something we talked about in class yesterday for the Physics 252 people. Now, which statement is untrue here? So 2 of these should be correct and 1 should be incorrect. You're looking for the incorrect statement.
Mine isn't showing up as being able to answer.
Most people have answered.
The internet.
It signed you out.
The internet's really bad right now.
Yeah, it's just loading.
Remind me after class so I can tell them we had problem at 11:43. Because they want to know when we have problems so they can try to figure out what went wrong.
We've had problems since 11.
Really? Writing this down so I don't forget.
Can you see my response?
I still do not have Aaron, Caitlin, or Gila.
I just used my credit card.
Oh, okay. So that would be 6F7 and 9-7 or whatever. Still not getting anything from you, Gila. Well, we've had enough and you answered the other one, so it's not going to hurt you. Okay, so our answers here were 0, 0. Hey, oddly enough, it says Gila didn't answer, but it says we had 20 people who answered. There's only 20 people in here. I'm really confused. Okay, everybody agreed. Why do you know that the first statement is true? What was the root of why momentum is conserved? Okay, no external forces was the condition because the root was Newton's second law. The net force is equal to the change in momentum over change in time. So if the net force is 0, momentum is conserved. So that idea of conservation of momentum still exists with the same condition because Newton's second law still applies, just not as force times ma. Question?
Part of Einstein's what were the postulates? That like the same rule.
Well, yeah, the laws of physics are the same in all reference frames. That's another way of looking at it. Okay, number 2, relativistic momentum is a vector. Well, yeah, that was just my statement. Momentum is still a vector. Number 3, relative momentum is PMV. What's wrong with that? Missing the gamma. Okay, so we got the important thing here about the gamma. Energy. This is a very famous equation, except for it doesn't have the 0 in it the way most people write. They just say equals mc squared. This is really, really important. It's not why Einstein got the Nobel Prize. That was for what we're going to study next week. But this set forward the whole world of nuclear energy. Einstein said that mass is just another form of energy. Up to this point, people thought that one of the fundamental rules of physics was that mass is conserved. You can't create or destroy mass. And Einstein said, with his work in relativity, that according to his determinations, mass is just a form of energy. And so you can look at me and say, man, that web kid's just got a lot of energy. But I conserve it nicely. I don't expend it on crazy things like running. But it's true. Mass is just a form of energy. Now, we're not talking about chemical energy, right? I mean, you can also say from a chemical standpoint, okay, so you stored up certain chemicals in your body that your body can then metabolize to produce energy, right? That's true. That's why our bodies store up fat. But this is not talking about chemical energy. It's talking about energy just because the mass exists. So you can take an inert object, something that's just a bunch of helium, and say just because it has mass, it has a certain energy. And if you do the right things, you could convert that energy from mass to some other form of energy, like kinetic energy. That's what you're doing in a nuclear bomb. You are converting mass into kinetic energy. And so what happens to the mass of the things that made up the original bomb after the explosion? It has to drop. There's less mass left. It's not because it spread willy-nilly hither and yon. It's because it was actually used up. The mass was used up and converted into the energy that made the big explosion. So that's what this equation equals mc squared is referring to. The actual energy something has because it has mass. And we call that the rest energy because even if it's at rest, it has this energy. For units of energy in relativity and moving forward, we like to use electron volts for energy. We've already talked about electron volt. An electron volt is the energy that one electron has if it goes through a voltage difference of 1 volt. And so we've already seen this calculation that 1 electron volt is 1.602 times 10 to the minus 19 joules because it's just the charge of an electron times 1 volt. But that's not the only thing we use here. We know that E is mc squared. And so if I express E in units of electron volts, then I should be able to calculate my mass in units of electron volts over c squared. Right? Electron volt over c squared is going to have to be a unit of mass. And that's exactly what we do. So we say, for instance, an electron has a rest energy of 511 kiloelectron volts. And so it has a rest mass. If it's at rest, its mass is 511 kiloelectron volts divided by c squared. And so that's what we're going to use in a lot of calculations for the mass of an electron. 511 kiloelectron volts squared. Now, an atomic mass unit, actually, let's go to the next, not the next slide, the one after that, was the momentum of an electron moving at a speed of 0.80 c in units of kiloelectron volts per c. Momentum in kiloelectron volts per c. I don't have time to do this calculation, so we're not gonna. But you would have to do P is equal to gamma mv. And so you just calculate the gamma, and then you multiply the mass, 511 kiloelectron volts per c squared, times the speed, 0.8 c, times gamma. I did want to do this problem, but out of time. So I will go through about 3 more slides in relativity, but next class period we'll move on to chapter 29. So you'll have to do, I'll put on Moodle, but you'll have concept coach questions for chapter 29 before Friday.